my shop. This is just going to be a quick video about why it's important to always test power transformers. Specifically, these are going to be low voltage doorbell type transformers, but this is just a general video on why it's important to always test these transformers before you use them. And I'm going to show you today how to test them, and I'm also going to show you a bad transformer that I found just by doing a routine check on a couple of them that I got the other day. So to start, a transformer is a very simple device. It consists of two copper windings, two or more windings, generally two for a simple step-up or step-down transformer, wrapped around an iron core. And the two windings are called the primary and the secondary. The primary winding is where you connect your main power, in this case would be 120 volts, to these two wires. Here, these two, and this is a ground. The secondary winding, or the output winding, is where either the stepped up, or in this case the stepped down voltage, or the lower voltage, will be outputted from the transformer. And in this case it is outputted on two screw terminals. These two particular transformers are designed to be used primarily on a doorbell type application. Anywhere from 10 to about 15 volts AC should be outputted at these screw terminals. So I'm going to show you how to test these transformers today. Now you can test them with two ways. One, you can apply an AC voltage to the transformer and measure the output. Or two, more importantly, you can check the windings with an ohm meter to check the resistance and also to check for any shorts to ground or leakage to the case of the transformer. And in this case, this one is not grounded, but it probably would be in the electrical box if it's mounted in one. But this one has an extra ground wire where you would connect it to your service ground. So I'm going to be using my triplet 630 here to test these transformers today. So I'm going to go ahead and get my test leads ready to go. And I'm going to set up the 630 to measure resistance. Hook up my leads. And then we're going to set it on the ×1 resistance scale. So when we short the two leads together, we should get full scale deflection. And we do. We'll adjust that so it's not pegging the scale. There we go. So we read 0 ohms when we short the leads together. Now that's what we should see right there, 0 ohms is a short. Now when we test this transformer, first we're going to test this one. So the first thing that we want to do to test this transformer is we're going to check across the primary winding. So we're going to check right across the primary. And that's good. We're reading about, well, let's see here. The scale goes, well, that's good. We know it's not 0 ohms, so we definitely have continuity there, and the resistance is not excessively high. So this transformer is reading good. And I will also be demonstrating on a digital meter as well shortly. So now we'll read the secondary, okay? Now the secondary reads a bit higher, but it's not 0, so it's certainly good, because it's supposed to read a little bit higher because it's less turns. Okay. So that this transformer is good and that both windings are intact. Now we're going to check from one winding to the other side of the other winding. So one side of the primary to one side of the secondary. Now we'll touch the other side of the secondary. No continuity. If we get continuity here, the transformer has an internal short and is defective. Now we'll go the other side of the primary to one side of the secondary and the other side of the secondary. Nothing. And now finally we'll check the primary to the case. Nothing, and let's see, nothing. So this transformer tests good. There are no shorts in the transformer and both windings read intact. And we'll show you this later. Now let's test this one. Now this one is the same type of transformer. You give two wires for the primary and two wires for the secondary. So we'll start by checking to see if the primary is intact. We'll go one side of the primary to the other side. And we'll hook on there. And now I'm not getting any reading, so let me make sure. I got a reading last time, I believe. Let's check ×10 scale. This one might have a different resistance. Last time I got a reading here, I don't know. Well, it seems to me that something is already going amiss with this transformer. Again, ×1. Nothing. So right away, we can tell something is wrong with this transformer by the reading on the primary. So now we're going to check the secondary. So we're just going to check across the secondary winding, and that is also reading bad. So something's wrong with this transformer. So now we'll check the ground wire to one side of the primary and the other side. Nothing, so that's good. Now we'll check ground to the secondary. Nothing and nothing. So there's no ground faults in the transformer, so you're probably thinking, what's wrong? Well, electrically in a transformer, none of the windings are supposed to ever be touching. So the primary winding is completely separate from the secondary winding in a transformer. The only indirect connection is through the actual iron core, that the magnetic flux causes a voltage to be induced in the other winding. So now we're going to go ahead and check one side of the primary to one side of the secondary. Nothing to the other side of the secondary. What's this? We have 0 ohms. We have a dead short. Let's check the other side of the primary to the secondary. Dead short. So this transformer is completely shorted out inside. So something has happened to this transformer to cause us to have a dead short between one side of the primary and one side of the secondary winding. So inside this transformer, the primary is somehow making contact with the secondary. And the scary thing about this is, if I hook this up to power, it won't trip a breaker and it won't cause any problems. I hooked this up and I measured the output voltage, and I expected to get anywhere from 10 to 15 volts depending on the input voltage. And I got full line voltage coming out of these screw terminals. And it didn't trip a breaker. And that is why you always want to check something like this. Because if this transformer was installed in a circuit and it was hooked up and your doorbell all of a sudden quit working, fried it, and you went to see if your breaker was tripped, it wasn't tripped, so you would assume this transformer would be okay to touch. You go up here to start unscrewing these normally low voltage terminals, you're going to get one heck of a shock if you have 120 volts sitting across these terminals. That is not supposed to happen. And I can go ahead and verify that with my DMM here, one of my digital meters. So I'm going to set this to ohms times 1. Okay, so just like the triplet here, I'm going to go ahead and connect this meter up, and we'll go ahead and repeat the tests with the digital meter. I hope you can see that on the camera. Let's see if I can zoom that in a little bit. I hope you can see that digital meter. Right now it's reading open. When we short it out, it goes to 0. So right now we're reading 0 ohms, which is a short, holding the leads together. And now open. So again, this transformer, let's check across the primary. And we read open. Okay. Let's check across one side of the primary to one side of the secondary. And we read a dead short, 0 ohms. 0 ohms. So an absolute dead short through this transformer. Now let's check the good one. We're going to check across the primary winding. Okay, we read about 94 ohms. That's good. Let's check across the secondary. We read about 2 ohms. And I misspoke earlier if I said that that resistance reading on the secondary was higher. It's actually a lower resistance, which would be normal since it's got less turns in it. So we read about 2 ohms there. That's good. Now the defective transformer, let's check the resistance on the secondary. Open. Now what I'm going to go ahead and do to demonstrate is I'm going to connect up the good transformer to AC voltage, 120 volts, and we're going to read the output voltage. So let me set this up to AC volts, and I might as well do it on the 630 as well. So let's go to volts and 200. So we're going to read the primary voltage first, and then we're going to, actually no, we're just going to read the secondary voltage. So 20 volts. Okay. So this is set up right now to read the secondary voltage coming out of this transformer. So I have 120 volts coming out of the variac over here, and that is going into the primary of the transformer. And I'll zoom out here so I can show you how I'm setting this up. So if we look right here, these clip leads are going to be at 120 volts potential, and I'm simply going to connect them across the primary winding of the transformer. Just like if it was hooked up to the wall. Make sure these don't short out. And we're going to put our meter across the output here, and we're going to read the secondary voltage, which should be around 15 volts or so, depending on what the primary is. So let's get a look at that meter. And now we're going to go ahead and energize the primary. Okay, the primary winding is now energized. I'm going to go ahead and hook the meter across the secondary. Now volts, let's see, 20 volts. So we're going to go ahead and read across the secondary winding. Okay, what's going on here? I'm getting, okay, the variac's hooked up. There we go. Sorry, the meter was just set on the wrong range. Yeah, I had that on the 10 volt range. Yeah, I'm just checking the meter here. So that's set correctly now. So we have 18 volts. So that's with no load on the transformer. 18 volts. Okay? So now we're going to go ahead. So this transformer is good. So we'll disconnect it. Okay, so this transformer is good. So now we're going to go ahead and hook up the defective transformer. Known to be defective, we'll de-energize for safety. And now we're going to take our known to be defective transformer, and we're going to connect it across the AC line. Same way we did with the first one. Making sure to not short out to anything. And now we're going to repeat the same experiment. And we're going to go ahead and connect, let's change ranges here. We're going to connect the meter to the secondary winding of the transformer, and we're going to read the output voltage. So here we go. Right now, this transformer is energized and it didn't trip a breaker. You wouldn't think anything is wrong until we read the output voltage. And look at that, 120 volts. Can you see that? We have 120 volts coming out of the output of this transformer. Isn't that something? Let's get right in on that meter. Now I'm connecting right across the secondary. 120 volts. De-energize. So clearly, something is clearly wrong with this transformer that we are getting 120 volts coming out of the secondary winding. That is not supposed to happen under any circumstances. So we now have proven that this transformer is defective. We input 120 volts on one side, we get 120 on the outside. Output. We should not be getting that. We should be getting anywhere from 10 to about 15 volts DC, and when it's unloaded it might climb to as high as 20 volts. So this is a bad transformer. Now, that was just a short video that I wanted to make showing why it's always important to check that, because like I said, the dangerous part about it is that did not trip a breaker. You could have had this hooked up to a power supply. Nothing would have ever detected it was wrong. And as soon as you went to go touch those output terminals, you would get a good zap. And if you were to go ahead and ring your doorbell, it would immediately probably fry the whole doorbell circuit. The solenoids for the bells and probably the button too. So right there is a very good reason why it's always important to check these things, okay? Because you never know what can happen. This transformer must have been overheated or something happened to it clearly to cause that internal short. And I just so happen to be checking these transformers, and luckily I have spares, but this one is no good. And even if I got this repaired somehow, I would never trust it again. Clearly a transformer should never do that, as the windings are completely isolated. So that was just a quick video I wanted to make on why it's always important that anytime you get any type of transformer, before you apply power to it, always check with an ohm meter or a continuity buzzer. Check the continuity of the windings, check the continuity of the windings to the other windings, and also, importantly, check the continuity of each winding to the case or the ground, because if the case isn't grounded and one of the wires were to touch this metal frame, whatever this transformer is mounted to would then become energized. But if it's grounded, then of course you would trip a breaker.